first speaker is Manush. He will talk about the reliability of cusp versus core and halo parameters in dark matter halos. Over to you.
Thank you. Am I audible? Okay, so I am Manush. I would like to thank the organizers for giving me this opportunity to present my work here. I'll be talking about the reliability of cusp and core as we infer it from the rotation curves. I'll start with a small introduction to the cusp core problem. As Matthew was explaining it yesterday, it is linked to the fact that gravity is scale-free, and the n-body simulations predict dark matter halos which are self-similar. So these are two plots from two seminal papers. The left-hand side plot is from the original paper of Navarro, Frank, and White, where they show the density profile of 4 halos, which are of 4 different mass. And you can see that they can all be described by one single functional form, which is the NFW profile. On the right-hand side is a plot from the Burkett in the same year. So he plotted the scale-free mass profile of offset galaxies from rotation curves. And you can see the NFW profile predicts a mass profile which goes like this. So there is a clear deviation in the central region from the predictions versus the observation. Burkett showed that these mass profiles can be better fitted by a density profile, which is code in nature, that at central region it goes as a constant density, as opposed to 1/r divergence observed in the NFW profile. And we can infer this cusp and core from the rotation curves. If the density goes as 1/r, then we will expect the velocities to go as square root of r in the central region. And if the density is constant, we expect the rotation curves to rise linearly with the radius. So here is an example of two rotation curves. On the left side is UGC 12632, which is a dark matter dominated galaxy. We can see in the central 3 kPa it can be explained by a square root of r rise in the rotation velocity. On the right hand side is another galaxy which is again dark matter dominated. Here you can clearly see that the slope of the rise is shallower and can be well fitted by a linear relation with the radius. It's not necessary that we have to infer the cusp and core from the rotation curve. We can also obtain it directly from the velocity fields observed from the spectroscopic measurements. For example, in the cuspy case, the constant velocity contours will be pinched in the center as opposed to the core profile, which will be almost parallel. In my work, I used SPARC galaxies for studying the cusp core problem. SPARC consists of high quality H1, H-alpha rotation curves. These are compiled from various observations, and they update the stellar profile using surface photometry at near infrared band. So the total rotation velocity can be decomposed into various components, one due to dark matter halo, due to gas disk, and due to the stellar disk. However, the luminosity of the stars, conversion of the luminosity of stars to mass has an uncertainty. So we have to multiply this with a constant factor of mass to light ratio. What it essentially does is scale the stellar component up and down. So given this mass to light ratio and assuming some density profile for the dark matter, we can fit the rotation curve and obtain the parameters of the dark matter, which essentially gives the dark halo of the galaxy. So these are few rotation curves from the SPARC catalog. There are 175 rotation curves in the SPARC catalog. I would like to point out some points like rotation curves have different density of data points in different radial scales. For example, in this rotation curve, there are a lot of data points in the central region. And there are also things like for some rotation curves, even at the last data point, the galaxy is still rising. As opposed to some rotation curve, we have flat part of the rotation velocity as well. Also, you can see that the error bars on these data are not uniform. They are radius dependent. And there are various scatters in these rotation curves also, which are important considering the size of the error bars. So as in all these, SPARC rotation curve has a diverse nature of rotation curves. And these SPARC catalog has been the testbed for various cusp core formation mechanisms which has been proposed. So the solutions, there are various solutions proposed for core cusp problem, and they can be all classified into two classes: the astrophysical process and particle nature of dark matter. In the astrophysical process, it depends upon the baryonic physics. Essentially, examples like supernova feedback or aging feedback comes under this class. And there are also solutions which depends upon the particle nature of the dark matter. For example, self-interacting dark matter, fuzzy dark matter, and so on. All these mechanisms proposes some or the other core profile for the dark matter halo. What we see is that from the rotation curves, you can differentiate between a Caspi profile and a chord profile, but often it's not possible to differentiate two chord profiles from one another. For example, in this case, the rotation curve of 583, you see that the NFW profile, which is the orange line, is not that good in fitting this rotation curve, whereas the DC14 and SIDM, DC14 is a profile proposed for the supernova feedback, and SIDM is for the self-interacting dark matter case. Both these chord profiles fit the rotation curve almost equally well. So you cannot use the goodness of the fit measurement to distinguish between these various mechanisms. So in my study, I use NFW to model the Caspi profiles. And for the chord profiles, I use a phenomenologically motivated profile, which is Burkett plus NFW. Essentially, the outer region of the halo is modeled as an NFW profile, and it's smoothly connected to the Burkett profile in the central region at this radius RC. We use these boundary conditions that density and mass at the radius RC is continuous, which makes our chord profile essentially a 3-parameter model. Now we go ahead and make mock rotation curves to study the reliability of cusp and core, which we can infer from the rotation curves. What we do is that we make rotation curves in various bins of masses. For a given mass, we use the mass concentration relation to obtain the dark matter halo. And then we use the stellar halo mass relation and various baryonic relations to construct their baryonic gas and the stellar disk components. So the total rotation velocity is shown here for various mass bins. And for each mass bin, we create rotation curves which extends up to different radius, which is basically the R last, the last data point up to which the rotation curve is available. And then we want these rotation curves to mimic the observed spark galaxies. So we obtain the distribution of the data points, the frequency of the data points, the scatter, the error bar, everything. We directly sample from the spark galaxies and input in our mock galaxies. And since we are doing a statistical analysis, we make various ensembles of these, various realizations of this. And so for in each bin of mass and R last, we create 100 rotation curves, where 50 of them are cusp and 50 of them are core. Here, the core profiles are shown in purple and the cusp profiles are shown in a green color. And then we go ahead and do a Bayesian analysis on all these mock rotation curves. We use nested sampling algorithm for doing so, which gives us the posterior and the evidence, which is the integral of the prior times with likelihood over the entire parameter range. This gives us the Bayes factor, which is basically the ratio of the evidence for obtained while fitting these rotation curves with core and the evidence which obtained by fitting these rotation curves with cusp profile. And the log of this Bayes factor can be used to find various evidence for the core. So we are basically testing our null hypothesis, which is the cusp, against a signal, which is that there is a core. And to define the reliability of the cusp core inference, we use this omega I parameter for each mock rotation curve. What we do is we just define it to be 1 if the input model could be recovered from fitting by doing Bayesian analysis and obtaining this model selection. And it is 0 otherwise. Then we obtain the reliability parameter, which is the average of this omega in single bin of M200 and R last. So this reliability parameter will have a value between 0 and 1. If it is 1, then it essentially says that all the mock galaxies in that bin could be successfully recovered. The original profile of the mock galaxy could be successfully recovered. And this is the result. What we see is that for the cusp core inference, the reliability parameter here, the reliability parameters are shown here. The dark region is the 75% reliable region, which is R being this R will be 0.75 there. It essentially says that in a given pixel, 3/4 of the mock rotation curves could give back the original model with which we made the rotation curve. What we see is that there is a sudden fall in the reliability parameter at this value of sigma naught. Sigma naught is the stellar surface density. So what happens is that here is that like for high values of surface density, the baryonic component will be dominating in the center. And by scaling it up and down, it can erase away the signature of the cusp and core. On the right-hand side, we also check the reliability of estimating halo parameters from these mock rotation curves. And here we see that there is a good cutoff in the reliability for various values of R last. This essentially says that we need an extended rotation curve if we have to model the M200 and C200 properly. Halo parameters are basically the halo mass and the concentration. So we also overplot the position of the spark galaxies in this. those galaxies which fall in the 75% reliable region of the left and the right plot are marked with stars. We find that there are only 21 rotation curves in the Spark catalog which falls in the 75 reliable region, where cusp core distinction and halo-parameter estimation can be obtained. Interestingly, this cutoff in the stellar surface density was already seen. So there are some works which shows that cores are generally found in galaxies which have surface density below this range. So we know right now it's not that the cores are there. Cores can also be there in the range where surface density is high, but we cannot statistically distinguish between the cusp and the core. And these are the 21 reliable rotation curves. We find that there are 5 rotation curves there, which can be explained with NFW. You don't have to invoke core profile to fit there with those rotation curves. And for the rest of the rotation curves, a core profile is necessary. And I will just quickly glance through it because it's an ongoing work. We could do a number of dark matter physics using these reliable rotation curves. Like we can study the diversity of the rotation curve, essentially probe the inner slope of the density profile. We can study the mass concentration and extend it to a very high precision to low mass regions. We find that the concentration has a correlation with the surface density, essentially saying that adiabatic contraction might have increased the concentration in these halos. And we can also probe the velocity distribution function of the dark matter. And we here show the halo to halo scatter in these rotation obtained from these rotation curves. We can also study the pseudo-space density of the dark matter, obtain the full 6-dimensional phase space density of the dark matter. And we can maybe even go ahead and probe this cross-section of self-interaction, assuming that these cores were probed. These cores were formed due to the interaction of the dark matter with each other. So that's it. I would like to thank the organizers once again for giving this opportunity, and thank you for your attention.
Thanks for the talk. Any questions?
So this reliability is very interesting. So I want to understand the way you generate the mocks. Do you account for non-gravitational forces in the inner parts of the disks, of the gas disks, due to gradient of pressure?
No, I don't account for that at the moment.
So there was a paper some years ago by Pineda et al. Who did hydro simulations, and then they performed mock observations of their hydro simulated galaxies. And they found that even though the hydro simulation was based on an NFW profile, which is CUSP, when they analyzed the mock observation using a rotation curve built in the standard way with only gravitational forces, you end up inferring that there is a core. So I'm not sure which way that will push your analysis. It is, I think, an important thing to consider.
Yeah, this is all given that our rotation curves are as good as it can get. And yes, these effects will actually affect the cusp core inference.
It may be worth just asking in what direction you would go, because would more rotation curves fall in the reliable range or less? I'm not sure.
I would guess that the reliability will be less again for the low surface density galaxies, because that's where observation will be tougher to obtain. Yeah, even I don't. I will check on that and I will get. Thank you.
Nice talk, Manush. So have you tried to look at correlations of the core sizes with other galaxy properties?
Yes, I'm working on it right now. And yeah, there are some interesting things like.
Okay, yeah, because then, you can comment about some of the degeneracies with.
So it's necessary to actually figure out the real mechanism for cusp problem, especially this detailed physics of how the cores are formed and properties of the core. I'm looking into it. I'll talk to you about it.
And you didn't find any evidence for anything which was steeper than an NFW, is that right?
So this code profile which we are using, it can actually fit even more cuspier profiles than NFW profiles, because you can adjust the central density accordingly. And so there are some rotation curves which are very steep in the center.
I see.
Which can also be fitted. I don't think it's there in this reliable galaxies.
Okay, thanks.
Any more questions? Okay, let's then thank the speaker.